Hello and welcome. My name is Alan, and today we are back with hopefully the final episode of Ideas and Opinions of Albert Einstein. Today we are doing the last little bit, finishing the last chapter. It's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pages more or less. So let's go ahead and hop into this. In Newtonian mechanics, space and time play a dual role. First, they play the part of carrier or frame for things that happen in physics, in reference to which events are described by the space coordinates and the time. In principle, matter is thought of as consisting of material points, the motions of which constitute physical happening. When matter is thought of as being continuous, this is done, as it were, provisionally in discrete structure. In this case, small parts, elements of volume of matter, are treated similarly to material points, or at least insofar as we are concerned merely with motions and not with occurrences, which at the moment is not possible or serves no useful purpose to attribute to motions, e.g., temperature changes, chemical processes. The second role of space and time was that of being inertial system. Inertial systems were considered to be distinguished among all conceivable systems of reference in that, with respect to them, the law of inertia claimed validity. In this, the essential thing is that physical reality, thought of as being independent from the subjects experiencing it, was conceived as consisting, or at least in principle, of space and time on one hand, and of permanently existing material points, more or moving with respect to space and time on the other. The idea of the independent existence of space and time can be expressed drastically in this way. If matter were to disappear, space and time alone would remain behind as kind of a stage for physical happening. This standpoint was overcome in the course of a development which, in the first place, appeared to have nothing to do with the problem of space-time, namely, the appearance of concept of field and its final claim to replace in principle the idea of a particle, material point. In the framework of classical physics, the concept of field appeared as an auxiliary concept in cases of which matter was treated as a continuum. For example, in the consideration of the heat conduction in a solid body, the state of the body is described by giving the temperature at every point of the body for every definite time. Mathematically, this means that the temperature T is represented as a mathematical expression, function of the space-time coordinates, and time T temperature field. The law of heat conduction is represented as a local relation differential equation which embraces all special cases of the conduction of heat. The temperature is here a simple example of the concept of field. This is a quantity or a complex of quantities, which is a function of the coordinates and the time. Another example is the description of the motion of liquid. At every point there exists in any time a velocity which is quantitatively described by its three components with respect to the axes of coordinate system vector. The components of the velocity at the point, field components, here also are functions of the coordinates x, y, and z, and the time t. It is characteristic of the fields mentioned that they occur only within a ponderable mass. They serve only to describe a state of this matter. In accordance with the historical development of the field concept, where no matter was available, there would also exist no field. But in the first quarter of the 19th century, it was shown that the phenomena of the interference and the diffraction of light could be explained with astonishing accuracy when light was regarded as a wave field, completely analogous to the mechanical vibration field in the electric solid body. It was thus felt necessary to introduce a field that could also exist in empty space. In the absence of ponderable matter, this state of affairs created a paradoxical situation because, in accordance with its origin, the field concept appeared to be restricted to the description of states in the inside of a ponderable body. This seemed to be all the more certain inasmuch as the conviction was held that every field is to be regarded as a state capable of mechanical interpretation, and this presupposed the presence of matter. One thus felt compelled, even in the space which had hitherto been regarded as empty, to assume everywhere the existence of a form of matter which was called ether. The emancipation of the field concept from the assumption of its association with a mechanical carrier finds a place among the psychologically most interesting events in the development of physical thought. During the second half of the 19th century, in connection with the researches of Faraday and Maxwell, it became more and more clear that the description of electromagnetic processes in terms of field was vastly superior to a treatment on the basis of a mechanical concepts of material points. By the introduction of the field concept in electrodynamics, Maxwell succeeded in predicting the existence of electromagnetic waves, the essential identity of which with light waves could not be doubted, if only because the equality of their velocity of propagation. As a result of this, optics was, in principle, absorbed by electrodynamics. One psychological effect of this immense success was that the field concept gradually won greater independence from the mechanistic framework of classical physics. Nevertheless, it was at first taken for granted that electromagnetic fields had to be interpreted as states of the ether, and it was zealously sought to explain these states as mechanical ones. But as these efforts always met with frustration, science gradually became accustomed to the idea of renouncing such a mechanical interpretation. Nevertheless, the conviction still remained, but remained that electromagnetic fields must be states of the ether, and this was the position at the turn of the century. The ether theory brought with it the question: how does the ether have or behave from the mechanical point of view with respect to ponderable bodies? Does it take part in the motions of the bodies, or do its parts remain at rest relatively to each other? Many ingenious experiments were undertaken to decide this question. The following important acts should be mentioned in this connection: the aberration of the fixed stars in consequence with the annual motion of the earth, and the Doppler effect, i.e., the influence of the relative motion of the fixed stars in the frequency of the light reaching us from them, for known frequencies of emission. The results of all these facts and experiments, except for one, the Michelson-Morley experiment, were explained by H.A. Lorentz on the assumption that the ether does not take part in the motions of ponderable bodies, and that the parts of the ether have no relative motions at all with respect to each other. Thus, the ether appeared, as it were, as the embodiment of a space absolutely at rest. But the investigation of Lorentz accomplished still more. It explained all the electromagnetic and optical processes within ponderable bodies known at that time, on the assumption that the influence of ponderable matter on the electric field, and conversely, it is due solely to the fact that the constituent particles of matter carry electrical charges which share the motion of time particles, or share the motion of the particles. Concerning the experiment of Michelson and Morley, H.A. Lorentz showed that the result obtained at least does not contradict the theory of an ether at rest. In spite of all these beautiful successes, the state of the theory was not yet wholly satisfactory, and for the following reasons: classical mechanics, of which it could not be doubted that it holds with a close degree of approximation, teaches the equivalence of all inertial systems or inertial spaces for the formulation of natural laws, i.e., the invariance of natural laws with respect to transition from one inertial system to another. Electromagnetic and optical experiments taught the same thing with considerable accuracy, but the foundation of electromagnetic theory taught that a particular inertial system must be given preference, namely that the luminiferous ether at rest. This view of theoretical foundation was much too unsatisfactory. There was no modification that, like classical mechanics, would uphold the equivalence of inertial systems. Special principle of relativity. The answer of the equation in the special theory of relativity. This takes over from the theory of Maxwell-Lorentz, the assumption of the constancy of the velocity of light in empty space. In order to bring this into harmony with the equivalence of inertial systems, special principle of relativity, the idea of the absolute character of simultaneity must be given up. In addition, the Lorentz transformation for the time and the space coordinates follow for the transition from one inertial system to another. The whole content of the special theory of relativity is included in the postulate. The laws of nature are invariant with respect to the Lorentz transformations. The importance of this requirement lies in the fact that it limits the possible natural laws of it in a definite manner. That, or what is the position of special theory of relativity in regard to the problem of space? In the first place, we must guard against the opinion that the four-dimensionality of reality has been newly introduced for the first time by this theory. Even in classical physics, the event is localized by four numbers, three spatial coordinates, and a time coordinate. The totality of physical events is thus thought of as being embedded in a four-dimensional continuous manifold. But on the basis of classical mechanics, this four-dimensional continuum breaks up objectively into the one-dimensional time and into three-dimensional spatial sections, the latter of which contains only simultaneous events. This resolution is the same for all inertial systems. The simultaneity of two definite events with reference to one inertial system involves the simultaneity of these events in reference to all inertial systems. This is what is meant when we say that the time of classical mechanics is absolute. According to the special theory of relativity, it is otherwise. The sum total of events which are simultaneous with the selected event exist. It is true in relation to a particular inertial system, but no longer independently of the choice of the inertial system. The four-dimensional continuum is now no longer resolvable objectively into sections which contain all simultaneous events. Now loses for the spatially extended world its subjective meaning. It is because of this that space and time must be regarded as a four-dimensional continuum that is objectively unresolvable if it is desired to express the purpose of the objective relations without unnecessary conventional arbitrariness. Since the special theory of relativity revealed the physical equivalence of all inertial systems, it proved the untenability of the hypothesis of an ether at rest. It was therefore necessary to renounce the idea that the electromagnetic field is to be irreducible, or is to be regarded as a state of a material carrier. The field thus becomes an irreducible element of physical description, irreducible in the same sense as the concept of matter in the theory of Newton. Up to now, we have directed our attention to finding in what respect the concepts of space and time were modified by the special theory of relativity. Let us now focus our attention on those elements, which this theory has taken over from classical mechanics. Here also, natural laws claim validity only when an inertial system is taken as the basis of space-time description. The principle of inertia and the principle of the constancy of the velocity of light are valid only with respect to an inertial system. The field laws also can claim to have meaning and validity only in regard to inertial systems. Thus, as in classical representation of physical reality, thus, as in classical mechanics, space is here also an independent component in the representation of physical reality. If we imagine matter and field to be removed, the inertial space, or more accurately, this space altogether with the associated time remains behind. The four-dimensional structure, Minkowski space, is thought of as being the carrier of matter and of the field. Inertial spaces with their associated times are only privileged four-dimensional coordinate systems that are linked together by the linear Lorentz transformations. Since there exists in this four-dimensional structure no longer any sections which represent now objectively the concepts of happening and becoming are indeed not completely suspended, but yet complicated. It appears, therefore, more natural to think of physical reality as a four-dimensional existence instead of hitherto the evolution of three-dimensional existence. This rigid four-dimensional space of the special theory of relativity is to some extent a four-dimensional analog of H.A. Lorentz's rigid three-dimensional ether. For this theory, also, the following statement is valid. The description of physical states postulates space as being initially given and as existing independently. Thus, even this theory does not expel Descartes' uneasiness concerning the independent or indeed the a priori existence of empty space. The real aim of the elementary discussion given here is to show to what extent these doubts are overcome by the general theory of relativity, the concept of space in the general theory of relativity. This theory arose primarily from the endeavor to understand the equality of inertial and gravitational mass. We start out from the inertial system S1, whose space is, from the physical point of view, empty. In other words, there exists in the part of space contemplated neither matter in the usual sense nor a field in the sense of the special theory of relativity with reference to S subscript 1. Let there be a second system of reference, S subscript 2, in uniform acceleration. Then S subscript 2 is thus not an inertial system with respect to S subscript 2. Every test mass would move with an acceleration which is independent of its physical and chemical nature. Relative to S2, therefore, there exists a state which, at least to a first approximation, cannot be distinguished from a gravitational field. The following concept is thus compatible with the observable facts. S2 is also equivalent to the inertial system, but with respect to S2, a homogeneous gravitational field is present, about the origin of which one does not worry in this connection. Thus, when the gravitational field is included in the framework of the consideration, the inertial system loses its objective significance, assuming that the principle of equivalence can be extended to any relative motion whatsoever of the systems of reference. If it is possible to use a base consistent theory on these fundamental ideas, it will satisfy of itself the fact of the equality of inertia and gravitational mass, which is strongly confirmed empirically. Considered four-dimensionally, a nonlinear transformation of the four coordinates correspond with the transition from S subscript 1 to S subscript 2. The question now arises, what kind of nonlinear transformations are to be permitted, or how is the Lorentz transformation to be generalized? In order to answer the question, the following consideration is decisive. We ascribe to the inertial system of the earlier theory this property. Differences in coordinates are measured by stationary rigid measuring rods. The difference in time by clocks at rest. The first assumption is supplemented by another, namely that for the relative laying out and fitting together of measuring rods at rest, the theorems on lengths in Euclidean geometry hold. From the results of the special theory of relativity, it is then concluded by elementary considerations that this direct physical interpretation of the coordinates is lost for systems of reference S2, accelerated relatively to the inertial systems S1. But if this is the case, the coordinates now express only the order of rank of the contiguity, and hence also the number of dimensions of the space, but do not express any of the metrical properties. We are thus led to extend the transformations to arbitrary continuous transformations. This implies the general principle of relativity. Natural laws must be covariant with respect to arbitrary continuous transformations of the coordinates. This requirement, combined with that of the greatest possible logical simplicity of the laws, limits the natural laws concerned incomparably more strongly than the special principle of relativity. This train of ideas is based essentially as the field is an independent concept for the conditions prevailing with respect to S2 are interpreted as a gravitational field without the question of the existence of masses which produce this field being raised. By virtue of this train of ideas, it can also be grasped while the laws of this pure gravitational field are more directly linked with the idea of general relativity than the laws for fields of general kind, when, for instance, an electromagnetic field is present. We have, namely, good ground for the assumption that the field-free Minkowski space represents a special case possible in natural law. In fact, the simplest case, con, uh, the simplest conceivable special case with respect to the metrical characters such a space is characterized by the fact that dx subscript 1 squared plus dx subscript 2 squared plus dx subscript 3 squared is the square of the spatial separation measured with a unit gauge of two infinitesimally neighboring points of a three-dimensional space-like cross-section. Pythagorean theorem, whereas dx subscript 4 is the temporal separation measured with a suitable time gauge of two elements with common x subscript 1, x subscript 2, x subscript 3. All this simply means that an objective metrical significance is attached to the quantity ds squared equals dx subscript 1 squared plus dx subscript 2 squared plus dx subscript 3 squared minus dx subscript 4 squared, as is readily shown with the aid of the Lorentz transformations. Mathematically, this fact corresponds to the condition that ds squared is invariant with respect to Lorentz transformations. If now, in the sense of the general principle of relativity, this space is subjected to an arbitrary continuous transformation of the coordinates, then the objectively significant quantity ds is expressed in the new system of coordinates by the relation ds squared equals g mu dx subscript 1 dx subscript 2, which has to be summed up over the indices I and k for all combinations 11, 12, up to 44. The terms g mu now are not constants, but functions of the coordinates which are determined by the arbitrarily chosen transformation. Nevertheless, the terms g mu are not arbitrary functions of the new coordinates, but just functions of such a kind that the form 1a can be transformed back into the first form by continuous transformation of the four coordinates. In order that this may be possible, the functions g mu must satisfy certain general covariant equations of condition which are derived by B. Riemann, more than half a century before the formulation of the general theory of equivalence, ds squared equals g mu dx subscript 1 dx subscript 2, describes in general covariant form a gravitational field of a special kind when the functions g mu satisfy the Riemann condition. It follows that the law for the pure gravitational field of a general kind must be satisfied when the Riemann condition is satisfied. But It must be weaker than the less restricting than the Riemann condition. In this way, the field law of pure gravitation is practically completely determined, a result which will be justified in greater detail here. We are now in a position to see how far the transition to the general theory of relativity modifies the concept of space. In accordance with the classical mechanics and according to the special theory of relativity, space-time, has an existence independent of matter or field. In order to be able to describe at all that which fills up space and is dependent on the coordinate space-time or the inertial system with its metrical properties must be thought of as an existing to start with, for otherwise the description of that which fills up space would have no meaning. On the basis of the general theory of relativity, on the other hand, space as opposed to what fills space, which is a pure gravitational field, might have been described in terms of g mu as functions of the coordinates by solution of the gravitational equations. If we imagine the gravitational field, i.e. the functions g mu, to be removed, there does not remain a space of the type ds squared equals dx subscript 1 squared plus dx subscript 2 squared plus dx subscript 3 squared minus dx subscript 4 squared. But absolutely nothing, and also no field, but at the same time also the topological and metrical structural properties of the manifold. A space of the type ds squared equals dx subscript 1 squared plus dx subscript 2 squared plus dx subscript 3 squared minus dx subscript 4 squared, judged from the standpoint of the general theory of relativity, is not a space without field, but a special case of the g mu field, for which the coordinate system used, which in itself has no objective significance, the functions g mu have values that do not depend on the coordinates. There is no such thing as an empty space, i.e. a space without field. Space-time does not claim existence on its own, but only as a structural quality of the field. Thus, Descartes was not so far from the truth when he believed he must exclude the existence of an empty space. The notion indeed appears absurd as long as physical reality is seen exclusively in ponderable bodies. It requires the idea of the field as the representative of reality in combination with the general principle of relativity to show the true kernel of Descartes' ideas. There exists no space empty of field. The general theory of gravitation. The theory of pure gravitational field on the basis of the general theory of relativity is therefore readily obtainable because we may be confident that the field-free Minkowski space with its metric in conformity with ds squared equals dx subscript 1 squared plus dx subscript 2 squared plus dx subscript 3 squared minus dx subscript 4 squared must satisfy the general laws of field. From this special case, the law of gravitation follows by a generalization which is practically free from arbitrariness. The further development of the theory is not so unequivocally determined by the general principle of relativity. It has been attempted in various directions during the last few decades. It is common to all these attempts to conceive physical reality as a field, and moreover, one which is a generalization of the gravitational field, and in which the field law is a generalization of the law of the pure gravitational field. After long probing, I believe I have now found the most natural form of this generalization, but I have not yet been able to find out whether this generalized law can stand up against the facts of experience. The question of the particular field law is secondary to the preceding general considerations. At the present time, the main question is whether the field theory of the kind are contemplated can lead to the go at all. By this is meant a theory which describes exhaustively physical reality, including four-dimensional space, by a field. The present day generation of physicists is inclined to answer this question in the negative. In conformity with the present form of the quantum theory, it believes that the state of a system cannot be specified directly, but only in the indirect way by a statement of the statistics of the results of measurements attainable on the system. This conviction prevails at the experimentally assured duality, corpuscular and wave structure, can be realized only by such a weakening of the concept of reality. I think that such a far-reaching theoretical renunciation is not for the present justified by our actual knowledge, that one should not desist from pursuing to the end the path of the relativistic field theory. Woo! We are finished. So, yeah. The final piece of information by Einstein, or his thoughts on things when it comes to the interaction of field theory with other things. You know, basically an interaction of all these ideas in different ways. So, yeah. But we are in with the system. I appreciate y'all for watching. I'll see you all in the next episode. Or there'll be no next episode, but later, y'all.